Morning children, Sairam. Children, in the previous presentation we all have learned about the Bohr's model of atom and the developments that led to the development of Bohr's model of atom. Now today we'll be discussing about the limitations of Bohr's model. See, limitations of Bohr's model led to the development of another quantum mechanical model of atom that we'll be discussing later. Today we'll be discussing only about the limitations of Bohr's model. Now see, the Bohr's model failed to account for the finer details of hydrogen spectrum which are observed by using sophisticated spectroscopical techniques. That means it was able to explain the hydrogen atom but not in detail. The second important limitation is that the model is also unable to explain the spectrum of atoms containing more than one electron. That means hydrogen atom is having only one electron. It was able to explain the spectrum of hydrogen atom, but other atoms which are having more than one electron, then Bohr's model is not able to explain the detail. Further, it was also unable to explain the splitting of spectral lines in the presence of electric and magnetic field. Now, in the presence of magnetic field, if the splitting takes place, it is called the Zeeman effect, which it failed to account for. And in the presence of electric field, the splitting of lines is called the Stark effect, which is again he is unable to explain that. Now, we'll be discussing about the developments leading to the quantum mechanical model. So, what were the drawbacks of Bohr's atomic model? First is that it could not explain the finer details of hydrogen spectrum. Second is that it could not explain the spectrum of those atoms which are having more than one electron. So, because of these drawbacks, the next quantum mechanical model was developed, and which all developments were there that led to the development of quantum mechanical model are the dual behavior of matter. Now, the Bohr's model was developed because of the dual behavior of electromagnetic radiation. But the quantum mechanical model is developed because of the dual behavior of matter. And second is the Heisenberg uncertainty principle. Now see, as the electromagnetic radiations are showing the dual behavior, that is the wave-like character and particle-like character. Wave-like character means they are associated with wavelength, frequency and all, and particle-like behavior was explained by Planck quantum theory. And according to Planck's theory, the electromagnetic radiations have particle nature. That means the energy is not absorbed or emitted continuously but discontinuously in the form of small packets of energy, and these small packets of energy are called photon. Yes, and the energy associated with each photon is equal to E is equals to h nu. This was Planck's theory. Now we are doing the development leading to the quantum atomic model, and this is saying that as electromagnetic radiations are having dual behavior, similarly the matter waves are also having dual behavior. Matter is also having dual behavior. Now, de Broglie in the year 1924 said that as radiations show dual behavior, similarly matter should also exhibit dual behavior. Who said this? De Broglie said this in the year 1924. That is, the matter should also behave like electromagnetic radiation, should show both the behaviors, that is the particle nature and the wave-like nature. Yes. Now, see, it means Just like a photon has a wavelength and momentum, electron should also have a momentum as well as wavelength. What is momentum now? Momentum is mass into velocity. It is denoted by P. Momentum is mass into velocity and is denoted by P. What de Broglie wants to state, it states that as the electromagnetic radiations are having dual behavior, similarly the matter should also exhibit dual behavior. That means just like the photon has a wavelength and momentum, electron should also have momentum. That means mass and velocity as well as wavelength. What is wavelength? Wavelength is lambda. That is, lambda is the wavelength. You all know what is meant by the wavelength. Wavelength is the distance between two adjacent rafts or two adjacent crest, if I have said reverse. Now, and de Broglie also gave a relationship that is called the de Broglie wavelength. Now, according to the de Broglie wavelength, we can say that lambda is equals to h upon m V. Lambda is equals to h upon mv. So, according to de Broglie, every object which is moving, which is in motion, have a wave characteristic. Actually, de Broglie is not talking about the heavier object. He was talking about only the lighter object, and said whenever an object is moving, it has a wave character, and the wavelength associated with this wave is given by lambda is equals to h over mv. Now, do you know what is h over here? Yes, try to find out what is h here. See, h here is that same Planck's constant whose value was 6.626 into 10 raised to the power. Yes. Now, see the wavelength which is associated with the ordinary objects which are moving is very small. Why? Because the mass is high. Why? Yes, because the heavy objects are having high mass, so the wavelength will be less. But their property, I'm sorry. So, smaller the object, higher will be the de Broglie wavelength. Heavier the object, smaller will be the value of de Broglie wavelength. Again, I am repeating. See, according to the developments that led to the quantum mechanical model were dual behavior of matter and Heisenberg uncertainty principle. Now, what is meant by dual behavior of matter? See, in the year 1924, de Broglie said that as radiations are having dual behavior, similarly matter should also exhibit dual behavior, that is both particle-like and wave-like nature. And it just means that photon has a wavelength and momentum. Similarly, electron should also have a wavelength as well as momentum. And de Broglie gave the relationship that is called lambda is equals to h over mv. So, according to de Broglie, every object in motion have a wave character, and the wavelength associated with the ordinary objects is very small. So, their properties cannot be detected. Why the wavelength associated with the ordinary objects are small? Because their masses are high. If the mass is low, then the wavelength will be more. Now, the second development that led to the discovery of quantum mechanical model is Heisenberg uncertainty principle. Now this principle was given by Heisenberg, so it is called Heisenberg uncertainty principle. Now the meaning of the word uncertainty you'll get to know in this principle. Now according to Heisenberg uncertainty principle, if a microscopic particle is moving, then it is impossible to measure simultaneously. Simultaneously means at the same time the exact position and momentum of electron or any other microscopic particle. So this Heisenberg uncertainty principle, it does not hold good for heavier objects. It is good only for the lighter object. And according to this, if a lighter object like an electron is in motion, then we cannot measure its position and momentum both with absolute accuracy at the same time. Now see why we cannot measure, because you all know that photons are these electrons are very small. In order to measure the position of the electron, suppose the electron is moving, and if we have to measure the position of the electron, then we must see that particle. In order to see the particle, light should fall on that particle, because without light we cannot see. When light falls on that electron, then the electron will gain energy and the position will change, because the velocity will also increase. So it is impossible to measure at the same time both position and momentum. If the position is certain, the momentum will be uncertain. If the momentum is certain, the position will be uncertain. See, mathematically it can be given as the equation delta x into delta p. Delta x is what? Position, and delta p is momentum, will be greater than equal to h upon 4 pi. That means it will not be exactly equal to h upon 4 pi, but it will be greater than, or it will be equal to h upon 4 pi. So we can also say that delta x into delta m into v. M into v is actually the momentum. Momentum is equals to mass into velocity is greater than h upon 4 pi. Taking the mass also to the right hand side, we get delta x into delta v is greater than equal to h upon 4 pi m. That means higher the mass, lower will be the accuracy. So children, these were the two developments that led to the development of quantum mechanical model of energy. Quantum means quantized energy is there. In the next presentation, we'll be studying about the quantum mechanical model, and till then you have to write down whatever is shown here in the form of presentations, in the form of these slides. Whatever is written here, you have to note it down in your fair notebook. These will help you in the form of your notes. Now again I'm repeating developments leading towards the quantum mechanical model of atoms. So what were the two developments? The first is the dual behavior of matter, that was given by de Broglie in the year 1924, according to which each material particle which is in motion should also exhibit dual behavior like the electromagnetic radiations are behaving. That means both the particle nature and the wave nature. And second is the Heisenberg uncertainty principle. Now for the dual behavior of matter, the wavelength that will be associated with the particle which is there in motion is also given by de Broglie and is called the de Broglie wavelength, and is equals to lambda is equals to h upon 4 h upon mv. Now you have to remember, higher the value of mass, lower will be the wavelength associated with it. That means for heavier object there is no significance of this law. It holds good only for the lighter objects. Now the second important development that led to the discovery of quantum mechanical model is Heisenberg uncertainty principle, according to which if a small microscopic particle is in motion, then we cannot measure simultaneously. Simultaneously means at the same time both position and momentum of these microscopic particles with absolute accuracy. And why we cannot measure this, I have already told you, because if we need to measure the position, then we need to let the light fall on it. If light falls on it, then it will gain velocity and the position will change, and the velocity will also change. So we cannot measure simultaneously both position and momentum of microscopic particles with absolute accuracy. Now children, I'll wind up with this for today, and in the next session we'll do the quantum mechanical model. Till then, kindly complete your fair notebook work. Thank you. Sai Ram.